Okay, so last time we talked about the differential rate law, which showed how the rate was dependent on concentration. And so today we're talking about the integrated rate law, which shows how the concentration changes over time. And so the reason why it's called the integrated rate law is because if you've done any kind of calculus anywhere, then you have probably heard the word integration or integral or something like that. The deriving of the equations that we're going to be talking about in this unit came from integrals and integration and stuff like that. You don't have to know that, but that's just kind of where it came from. You just have to be able to use the equations. So we're dealing with different things. So instead of dealing with rate and concentration, we're dealing with concentration and time in the integrated rate law. And so the way that you figure out if it's first order, second order, or zero order reaction is different than it was with the differential rate law. So it all has to do with the graphs of different things. So for a first order graph, if you plot, a first order reaction, if you plot the natural log of the concentration of A versus time, it will give you a straight line. Now I know logs and natural logs and all that stuff are not people's favorite thing to do. The good news is that even though we use them in here, pretty much the extent of it is just to punch it in your calculator and get the natural log or whatever. Okay, so if it's a first order reaction, if you plot the natural log of the concentration versus time, you'll get a straight line. If it's a second order reaction and you plot 1 over the concentration of A versus time, you'll get a straight line. If it's a zero order reaction, just simply plotting the concentration versus time data will give you a straight line. And so basically the process of this is you're going to go through, and this is why having a graphing calculator is helpful, is you're going to have to look at 3 different graphs based on the data you're given, and the one that gives you the straight line will tell you which order the reaction is, and then you can go through and write equations and stuff from there. So it's that part that is the hard part. Okay, so let's talk about those integrated rate law equations and then also something called half-life because it goes along with this as well. All of these equations in your book are summarized on page 548. So if you want to write down that page number, or if you have a book, open up to that page number. You'll see them all in a little blue box. Okay, so there are integrated rate law equations for first order, second order, and zero order. There aren't any really for third order. You don't have that. And so you pretty much have to memorize what they are. You have to memorize that if it has the natural log, then it goes with a first order reaction. And you can, go from up here. If it has the 1 over the concentration, it goes with second order. And if it doesn't have either of those things, then it's a zero order reaction. The good news is that on your reference sheet that they give you on the AP test, there's a little section here on kinetics, and they give you some equations. They don't give you all of them. They give you some of them, but they don't tell you if they're first order, second order, zero order. So you have to be able to identify which one goes with which. Okay, so first of all, if it asks you to write out the integrated rate law equation, once you figure out that it's a first order reaction, then this is simply the equation that you're going to write out. The natural log of, in this case, the concentration of A. So this is the concentration at time t. So like whatever time it is, if it's asking you to solve for the concentration at 100 seconds, then you would plug in 100 for time. T represents time. K is still the rate constant. And then this little A over here with the 0 next to it, that represents the initial concentration of A. So how much A did you start with? That's what gets plugged in there. Now, in addition to the rate law equations for first order, second order, and all that, for the integrated rate law, there are half-life equations that go along with that. First of all, you have to know what the half-life is. Have you heard the term half-life before? I think you have. Okay, half-life, the time required for a reactant to reach half of its original concentration. So there are equations that have been derived for each of the different integrated rate law orders. You don't need to know how they got derived. You just have to be able to plug them in and use them. Okay, so the half-life for first order, if it's a first order reaction, the half-life is equal to 0.693, which comes from a natural log of something, over K, the rate constant. And then that gives you the half-life. Okay, over here for second order, we're just going to write out the equations. And again, these are the equations that are just on page 548. And then we'll go through the process of what an actual integrated rate law problem looks like. Okay, second order reaction, the integrated rate law equation is 1 over the concentration of A equals the rate constant times time plus 1 over the initial concentration of A on all the integrated rate law problems, you only have one reactant. So it's whatever that one reactant here that gets plugged in for A. The half-life is 1 over the rate constant times the initial concentration. Okay, for zero order, the integrated rate law equation is concentration of A equals negative K times T. T is the time plus the initial concentration. Okay, so you'll see that like the format of all of these equations is all the same. So they all start with, something to do with the concentration. So with zero order, it's just the concentration. Second order, it's 1 over the concentration. With the first order, it's the natural log of the concentration. They all have the same format. And you'll kind of notice that they're in the format of y equals mx plus b. So they're all within that format because we're going to be dealing with graphs that give you straight lines, and whichever one gives you the straight line is the one that tells you the order of the reaction. So the format of all of them is the same. The half-life equations are different. So for zero order reactions, the half-life equation is the initial concentration of A over 2 times the rate constant.
I'm confused. Do we have 2 formulas for each one? Or?
Well, there's just 2 different types of questions. Some questions will ask you for half-lives, and so you have to use these equations to calculate the half-lives. Some equations will, or sometimes they'll just ask you to write out the integrated rate law, and that's what these are.
Okay.
So I'm just throwing out the equations right now. Now we're going to actually solve an integrated rate law problem using all of this stuff. So here are the steps. Jot down these steps, and then we're going to go through them in an example, and I'll show you how to shortcut a little bit, at least on your calculators. Okay, so here we go. The step in an integrated rate law problem, just to give you an idea, is, don't write this down yet, but you're going to be given the equation. You're going to be given a chart that has the concentration of the reactant over time. And so, because the integrated rate law is going to show how those things are related to each other. And so with that data, what you're going to have to do is you're going to have to calculate the natural log of the concentrations, calculate 1 over the concentrations, and then graph all 3 graphs. That's if you don't have a graphing calculator. You have to do all of that. That's why it takes extra time if you don't have one. The graph that gives you the straight line is going to tell you what the order of the reaction is. Okay, and then if it's, well, we talked about that at the beginning of the notes. If it's the one with just concentration that gives you the straight line, it's 0 order. If it's the 1 over the concentration that gives you the straight line, it's 2nd order. And then if it's the natural log graph, then it's 1st order. And then once you know what the order of the reaction is, then you can write the integrated rate law equation just based off of the formats that I gave you earlier in the notes. And then if it asks you to calculate, half-lives or whatever, then you can do that. All right, so let's go through all those steps, and I'll show you how to do it on your calculators too. So here's the example. Go ahead and write this down. We've got this equation, 2N2O5, as my reactant over on the product side, 4NO2 and O2. I have a concentration of N2O5 at all of these different times, and so we need to figure out what the order of the reaction is first. if you do not have a graphing calculator, what you would need to do is you would need to go through this table and you would need to calculate the natural log of all of these numbers. And so you would get all these numbers that represent the natural logs of the concentration. And then you would have to do 1 over the concentration of N2O5. So you would have to calculate 1 over all of these numbers and get a whole new data or a whole new section of your chart. And then you would be plotting 3 different graphs. Okay, when the 3 graphs are being plotted, it's good for even if you do have a graphing calculator, don't just tune out, because it's good for you to know kind of what your calculator is doing for you, basically. You're going to have to plot 3 different graphs. One is going to have the concentration over time, one is going to have the natural log of the concentration over time, and then the third graph is going to have 1 over the concentration over time. 3 graphs. 2 of them will give you like curvy lines, 1 of them will give you a straight line. The straight line one tells you what order the reaction is. This is 0 order, 1st order, 2nd order. Okay, so whichever one gives you the straight line is the one that you know represents the order of the reaction that you're dealing with. The question is still asking us, I mean, it's very much like the questions of last night's homework. It says determine the rate law and the value of K. We're just doing it differently because we're dealing with different data. We don't have any reaction rates or anything like that. We just have concentration and time, so we have to do it differently. So here's how you're going to do this in your graphing calculators. Ready? First thing you want to find is your stat button right here. And then again, this is just like you guys with 84s and 83s and maybe 86s will have similar buttons. If you're on 89, hopefully you can find that somewhere. And I'm just going to jot down these steps over here to the left. Okay, so stat first, you're going to hit edit. Okay, so you'll enter on edit. When you get there, you're going to have all of these different lists that you can fill in. Okay, now if there is anything in your list right now, then you're going to go up to the top, and even if you don't have anything in your list, listen, okay? So I have stuff in my L1, my list 1. I'm going to highlight my L1 and hit clear. Do not hit delete, because if you hit delete, then it deletes L1 completely and you don't have an L1 anymore. So just hit clear and then down arrow and it'll clear it all for you. Okay? So you want to start out with everything clear. Now what you want to do is in L1, you want to type in all of the times. Okay, so go ahead and do that right now. So L1 represents all my times. So 0, 50, 100, 200, 300, and 400. Oops. Do you guys have 89s?
Yeah.
If you guys have, who has 89s? There's just like a few of you, right? Do you guys want to like all go sit over there? So, or are you guys good? You guys good working together, and you guys are good working together? Okay, that's fine. I just wanted you guys all to make sure that you guys find the thing you're looking for. Okay, in list 2, go ahead and type in the concentration numbers. So the other numbers that are in this chart is going to go in list 2. So 0.1, 0.0707, 0.0500, 0.0250, 0.0125, and 0.00625. Okay, that is list 2. In list 3, are you ready? You have list 1 and list 2 entered. In list 3, go up to the top, highlight L3.
That's supposed to be a natural law.
Yeah. Highlight L3 and then hit enter. If you hit enter, the little cursor will start blinking down here at the bottom. And if you get that cursor blinking down at the bottom, what you can do is instead of having to calculate the natural log of all the concentrations, you can just actually type in natural log. So you punch in your natural log button. And then if you go to second list, which is right above your stat button, highlight L2 because L2 is your concentration. Hit enter. Let me do it again.
Yeah.
Okay. Natural log, and then second list, which is right above stat, L2. Okay? That'll give you the natural log of L2, and when you hit enter, it'll natural log all of those concentrations for you, and it'll fill it on your list 3. And if you're on a different calculator, you're going to have to kind of work through and find some of your stuff here. List 4, go over to list 4. Cursor up so that you have list L4 highlighted. Hit enter so that your cursor goes down to the bottom. And then you're going to type in 1 over second list L2. So then you get 1 over L2. Hit enter and it does 1 over all of those concentration numbers for you. Okay, so now I have 4 lists. I have L1 represents is my time that I typed in. L2 is the concentration values I typed in. L3 is the natural log of the concentrations. L4 is the 1 over the concentrations. Yeah. Okay. So if you go to L4 and you hit enter right here, I'm just going to clear them. 1 over. And then anytime if you just want to type in L1 or L2. Or I forgot. I knew I had this. If you just have it right here instead of having to do that, you can just go to right here above the 2 button is L2. So you just hit second L2. That's better. I was looking for that yesterday. I didn't see them until just right now. I knew they were there, but I couldn't. I don't know. Anyways, I'm crazy. So then you just hit enter, and then it's there. Okay? All right. And I think on 89, I think you actually just type it in or something fancy. All right. Now that you have that, okay, I have all of these lists. And yes, you could go through and you could actually have it graph it and do all of that kind of stuff. And you could see which graph gives you the straight line and which one doesn't. And the one that gives you the straight line is the order of the reaction. But sometimes they're like really close that you can't tell. So there's a little shortcut way to figure out which one is the straight line. So here's the shortcut without graphing it, okay? You are going to go to, again, your stat button. So here's my figuring out what's a short line, okay? Or what's a straight line. Stat. And then you're going to go over to tests. So I'm going to arrow over so that my tests are highlighted. And you are going to find, and on all of them, depending on how it's programmed, it's like it could be a different number or letter. What you're looking for is it says lin reg, like for linear regression, and then TINT. So mine is all the way down to letter G. And you might have one that looks a little bit different, but that's kind of what you're looking for. Did you find that? Okay, you hit enter on that. And what you're going to do here is where it says X list and Y list, you're going to do all of your different combinations. So like the 3 graphs that you're doing, L1 is always the X-axis. So you're going to be looking at L1 and L2 graph, L1, L3 graph, and L1, L4 graph. And what you're going to look at is you're going to look at something called the R-squared value. Quite honestly, I don't even really know what that means. But I do know that it's a shortcut for figuring out which one is the straight line. Because the R-squared value that's the closest to 1 is the straight line graph. And so if I type in, I'm just going to do them in order. If I go L1 and then L2, so I just hit second L2 right here, and then go down to calculate, it's going to give you a whole bunch of numbers right here. Okay, and you're going to have to arrow down to get your R-squared value. R-squared value is right there. Okay, so my R-squared value for list 1 and list 2 graph is 0.887.
Wait, you go down to where when you're on the L and regular T integral?
Okay, right. Okay, let me go there. Let me go there. Right here. I know, you're right here. You're right here, right? That's what you're asking me? Okay, so you typed in L, you have L1 and L2?
Yeah.
So then you just go down to calculate, and then you just hit enter. And you guys on different calculators, you'll have different menu options and stuff, but look for, there should be something that says something like this. Okay, and then you find that R-squared value. Then you go back to where we were. So stat, tests, your linear regression, and then you do L1 and L3. And scroll down to calculate. Ooh, yes. Oh, and then that just means that one's a straight line. Okay, this one gives me a straight or a R-squared value of 0.999. And then you would do it again for L1 and L4, and you would look up your R-squared value, and it would give you 0.88. Remember this one, L2 is my concentration, L3 is my natural log of the concentration, and then L4 was my 1 over the concentration. So the one that gave me the R-squared value closest to 1 is the one that represents the straight line. So it's the graph that had the natural log of the concentrations. And so that is my straight line graph. Natural log graphs that give you straight line represents a first order reaction. Once you have that part figured out, that's the hardest part, is figuring that out.
Wait, how do you know if which one's natural log, which one's 1 over?
Well, because in list 3 we typed in the natural log, and then in list 4 was 1 over and all that stuff. Once you figure out that it's first order, and we'll have time hopefully to go through your calculators today before you leave, but once you figure out that it's first order, then it's asking you to write out the integrated rate law. So the rate law equation for the first order graph is just, you go back over here to the ones that we talked about. So here's my equation for the integrated rate law for first order. And instead of A, I just plug in the concentration of whatever my reactant is, and then that's it. So it would be the natural log of N2O5 equals negative KT plus the natural log of N2O5 with that little 0. That means the initial concentration. So that's the integrated rate law equation. That's it. Okay, so the whole process, the hardest part is getting everything into your calculator, figuring out which one gives you the straight line graph. The straight line graph tells you the order of the reaction, so you can now write that. The regular rate law, the differential rate law, like the one that we did on Tuesday, if I were to write that out as well, would just be rate equals its first order, so it would be K times N2O5 with just, I mean, a 1, but you don't have to write the 1. It's a first order reaction. So that's it. Now, the other part of the question is to find the slope. Or not to find the slope, but to find K, which is the slope. It says to determine the value of K with units. The absolute value of the slope equals K. So, I mean, you can go through and you can calculate the slope based on your data points, but if you already have, so this is my data for the graph that gave me the straight line because my R-squared value is 0.99. If you scroll up to B, this is all these equations are in the format of y equals mx plus b. So the b is, or the, why did I, no, that's not right. Oh, they have it written backwards. Oh, it's a plus bx. So b does represent the slope. So you're going to look for b, and b here is negative 0.00693. So the absolute value of that number is equal to k. So that is then 0.0069. It's a first order reaction, so the units are inverse seconds, and so that's your k value. So then if you're using your calculators, you don't even have to do anything special to solve for k. You can just find it in your little calculation. Is what? That is what I had for b, 0.0069. They had their equation. I said y equals mx plus b because that's just the format in my head. But
And that value's for L3, right?
that value's for L1 and L3. Are you on L1 and L3? That's why. Yeah, so you have to look at the b value for the one that gave you the straight line. Okay? Okay, let me talk about, we'll have time to go back and, work on this as you guys start on your homework, but let me talk about one other type of problem that doesn't require any fancy graphing calculator stuff. Let's just do, we're going to do A and B here because C and D it's kind of repetitive, but it's more of like a half-life application and the wording of the questions. So go ahead and write this down and then we'll do it, and then you guys can start your homework and I can come around and work with you specifically on your calculators if you need to on that.
Okay, well, if you didn't have a calculator, how would you
So you would calculate slope, which would just be like change in y over change in x.
Yeah.
So you would just have to do it that way. Wow, bless you. Okay, so in this question, a first order reaction is 38.5% complete in 480 seconds. Calculate the rate constant. Well, the first thing, you need to pay attention to everything that it's telling you in the problem. First of all, it tells you that it is a first order reaction. So what you're going to start with is you're going to start by just writing the integrated rate law equation for a first order reaction, which is the one that we just talked about. So natural log of the concentration, I don't know what it is, they don't tell me what it is, so I'll just leave it empty, equals negative KT plus the natural log of the initial concentration. Okay, so I don't actually have amounts. I don't have concentration values in molarity, but what I do have is I have percentages to work with. So this is how much you have left, this is how much you have to start with. So whether you have actual molarity concentration values or you have percentages, you can plug them in either way. So before any of it reacts, I have 100%, right? So what I start with is always going to be 100%. What I have left is going to be, in this case, 100% minus, it says it's 38.5% complete, which means that 38.5% of the reactant has reacted and isn't there anymore. So then I'm going to subtract that and get 61.5% of my stuff that I have left. So I can take percentages and just plug those in as concentration values because of the fact that, you know, it'll work out whether it's molarity or percentages. So then I can just go ahead and plug in the natural log of 61.5. I can just do parentheses equals negative K, and that's my percentage left after 480 seconds. And then plus the natural log of 100 because that's my percentage that I'm starting with. Okay, natural log of 61.5 is 4.12. That equals negative K times 480. And then the natural log of 100 is 4.61. So I'm trying to solve for K. It asked me for the rate constant. So in order to do that, I've got to subtract 4.61 from both sides first. And you get negative 0.49 equals negative K times 480. And then when you divide 0.49 divided by 480, you get negative 0.001. That equals negative K. So then K is just 0.001. You should have proper units. This is a first order reaction, so it's inverse seconds as the units. Units for K values are the same here as they were for the other one, whether it's first order, second order, or whatever. Okay, so that's the trickiest thing, is just dealing with the percentages and knowing what to plug in here, that you always start with 100% and then however much you have left is what goes over here on this side. Sometimes you'll be asked, once you find K, they might ask you then to figure out, well, how much is left after 1,000 seconds. So once you have K, you can plug in your 1,000 seconds, your initial concentration, and you can solve for how much is left. How do you get rid of the natural log? What's the inverse of the natural log? Yeah, e to the x, right? And it's right above your natural log button. So like if you had, this is just kind of a side note, but if you were trying to find the natural log of x equals whatever number, I don't know, whatever number, 2.3 or whatever, then you would do e to the 2.3 equals x, and then that x would be here. Okay? That's it. I won't even do b because it's asking you to calculate the half-life, and it's just the half-life equals, that's just plugging it into the equation. So if you have the equation, all you have to do is plug it in. So your 0.693 over k, and we solved for k. Just gets plugged in there. Okay, half-life is normally in seconds. Sometimes it'll be in minutes. Just pay attention to what units they give you to work with in the problem.